Up until now, all of the signals that we've been analyzing have been periodic signals. And it made some degree of intuitive sense that you could create a periodic signal out of a sum of cosines which are periodic. Today we're going to look at what happens when you try to work with a aperiodic signal, a signal that never repeats itself. So what we're going to do is we're going to start with something that we understand, which is a periodic signal. So let's go ahead and draw a set of axes, and let's concoct some periodic signal x of t. And the particular shape doesn't matter because this is just a little bit of a proof of concept right now. So I'm going to draw some sort of periodic signal, and let me just draw a couple periods here. So it extends in every direction. And for the sake of argument, we're going to say that this thing has a period of t seconds. Okay, so some number t, every t seconds this thing repeats itself. Okay, so if we think about what the Fourier series of this signal is going to look like, we know that it's going to consist of harmonics, and the harmonics are going to be, so let me just make a plot. If this is a plot of the magnitudes, we know that the harmonics are going to be at integer multiples of 2 pi over t. All right, that's a concept we've seen over and over again. So for example, we know the first harmonic will be at 0, and the second harmonic, sorry, that's the 0th harmonic is at 0. The first harmonic is at 2 pi over t. The second harmonic is at 2 pi over t times 2. And the third harmonic, let's put it over here, 2 pi over t times 3, and so on. Okay? And the specific heights of the sticks just has to do with the specific signal that you're taking the Fourier transform of. Now, what if we play a little mathematical trick where we take the exact same signal, oops, let's do my axes in black. Let's take the exact same signal, and the only thing we're going to modify about it, we're going to keep the basic shape the same, and we're going to increase the period. Okay? So we're going to keep the periodic signal itself, like the basic shape of it, the same. Okay, but we're going to increase the period. So now, whereas before we had t seconds was the period, now we have a new value of t, which is bigger. Okay, oops. So what happens when in the frequency domain when t gets bigger? Well, it should seem reasonable enough to expect that as t gets bigger, the harmonic frequencies, which are integer multiples of 2 pi over t, those get smaller. So what we'd expect to have in this case is we would expect to have all the same sticks, all right, except now when I space them 2 pi over t apart, because t got bigger, that means 2 pi over t is smaller. Okay, so this is now my 2 pi over t. 2 times 2 pi over t, and now 3 times 2 pi over t, and so on. Okay, so as t gets bigger, these sticks get closer together. And if that makes sense, then I'll ask you to consider the final step, which is what happens in the case when we let the period get so big that eventually we let it drift to infinity. And when we do that, what we finally wind up with is a signal that never repeats itself. All right, now we say x of t is aperiodic. It never repeats. Okay? It repeats, but the repeat doesn't occur until t equals infinity, which never happens. So it's a bit of a mathematical trick, but it's a pretty helpful mathematical trick. So what happens in the frequency domain? Well, unsurprisingly enough, what you can imagine happens is that as t goes to infinity, 2 pi over t, the spacing between these harmonics, that goes to 0. And so instead of having a bunch of discrete sticks, those discrete sticks now are placed so closely together that they effectively now form a continuous function with respect to frequency. Okay? So before we had discrete values of A, one for each harmonic number n, and now we have continuous values of A. Okay, and instead of A being, there's no harmonic anymore. There's no n equals 0, n equals 1, and so on. Now we say that A is a continuous function of frequency. So another way to think about this is that whereas before, when we were dealing with periodic signals, we could take a periodic signal and express it as a sum of cosines whose frequencies were 2 pi over t times n, and then it would have been times t. Okay, and then of course there's a magnitude and a phase, but just right now I'm trying to make a point about how the cosines themselves are constructed. Let's not worry about the amplitude and phase yet. Now I'm telling you that the aperiodic signal, the aperiodic x of t, it's not a discrete sum of cosines anymore. There's not only infinite cosines, but they're infinitely spaced closely together. So now really what I'm doing is I'm integrating. I'm still taking cosines of frequency omega t, but instead of adding together a bunch of discrete ones, I'm doing it for an infinite number of infinitely closely spaced together omegas. Okay? So it's still a sum of cosines, it's just a sum of so many cosines that it's now an integral. Okay, and then for each frequency, there's going to be, so let me make myself a little bit more room. For each frequency, there's going to be an amplitude and a phase, where the amplitude and the phase come from A of omega, which is what you see in the plot above. Okay, if you take the magnitude of, it's the same as before. If you take 2 times the magnitude of A of omega, you get K. And if you take the angle of A of omega, you get the phase. Okay? And the formula that we have for A of n is the same formula that we've been dealing with all along. And that formula is simply A of omega equals the integral. Now before we had 1 over t, where t was the period. Now there is no period, so we're just going to omit that. We're going to integrate over all time. Before we were integrating over one period, but now one period is basically all time. And then everything else is the same. X of t e to the minus j omega t dt. Okay? And that is your Fourier transform. Okay, let's write that out. That's the definition of the Fourier transform. So again, the take-home message of this video is that once you transition from periodic to aperiodic or non-periodic signals, everything else stays the same. I mean, essentially this is the same formula we had before, but the biggest upshot is that your frequency is no longer a discrete function of frequency. It's now a continuous function of frequency.